Okay, so this is an example of one of these box problems. And in this case, we're starting with, say, a piece of, I don't know, piece of wood, or actually probably not wood. It had to be metal or something that can fold, or paper, or pliable plastic. So we have a square. We're starting with a 36-inch by 36-inch square of, let's say, metal. And we're allowed to cut 4 square notches. So the notches are going to basically allow us to then fold along the creases that I'm now drawing. Alright, these are the creases, and then so this part is going to get cut, or maybe we're just going to cut here and then use that to fold and make a tab. But mathematically, we're cutting them out. Okay? So what's happening here is then we're going to fold up the sides, and we're going to have a little ashtray or something. Well, it's not going to be an ashtray if it's 36 by 36 inches, but anyway. So this distance that we now get is going to be 36 minus 2, let's say it's x, whatever variable we want to use. And this variable is x. So those x's were just cut out marks. Now I'm going to call this letter x. And x is the size of the square we're cutting out. So in this case, we have a volume now. Volume of the open box. There's an open top. Volume of the box is 36 minus 2x is squared is the square on the bottom, and then times x. That's the volume of the box. But the surface area, the surface area is going to be 36 minus 2x squared, but not times something else. It's still the square on the bottom. Then we're going to take 4 copies of this, and this is x by 36 minus 2x. So it's going to be plus x, well, how many of them? Plus 4 times x times 36 minus 2x. Okay? So that's going to be the surface area. And the question is, we're going to either be asked to maximize something or minimize something, right? This particular question is asking us to maximize the box volume. But this is not a calculus class. If it were a calculus class, we could find it using calculus. But we're going to use numerics and what you know about cubics get the answer to within x is plus or minus 1/2 unit. In this case, the units are inches. Okay? So this is a little challenging because if you recall, all the problems we've done up to this point are just parabolas, and we just have to find the vertex, and that automatically gives us the max or the min depending on the problem. The setup here is the same, but what we're going to do is we're going to go through the same process we did with the parabola, but then we don't have a vertex. We're going to have to kind of sketch a plot. And based on our sketch, it should give us some intuition about where to start looking for a maximum value. Once we have a good idea of where to look, we poke around a little bit, and then we'll bracket this value, and you'll see how we do that. Okay, so let's take this piece, the volume. Okay, we want this volume here to be maximized. So this thing is we wish to maximize. And this piece we don't need for this problem. Okay, it doesn't even factor into this problem. Okay, so we're going to take a copy of this and we're going to put it down below. There we go. Okay, so what's going to happen? Well, let's actually plot this thing first. So we know that if 36 minus 2x equals 0, that's the same as 36 equals 2x, or 18 equals x, but this is a double root. So we use our little plot tools that we've been learning. Here, if x equals 0, we have a single root. Okay, so we wouldn't have been able to really plot this if I had expanded this whole thing. The only reason we're able to plot this at all is because it's already in a really nice format for us. We have a single root at 0, and somewhere over here we're going to label it 18. We have a double root. And this thing, well, you got to think through this a little bit. Is it going to end up with a minus x cubed at the beginning or a plus x cubed? It's got some coefficient out front, but I don't care about that. I just want to know about the sign. And we look and we say it's minus 2x, but it's squared. So if you FOIL that, that L is going to be 4x squared. So it's going to end up being 4x cubed. So this whole thing is going to start 4x cubed, da 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 da. That's all I care about, that it's positive. So then I'm going to try to guess what this looks like, but it's going to be a normal cubic, a typical cubic, but it's going to be situated in such a way that we have a double root here at 18. Okay, so it's kind of hard to sketch these things without making a mess of the paper, but there we go. We just kind of visualize this. Okay, that's not too bad. Now, the way we draw them, we often put, the max right at 9. And that's not really what happens. It's going to be shifted a little bit to the left, right? But it's not going to be too far off. Here's the 9, and you know that the max has to be, somewhere in this vicinity. All right, so now that we have that information, let's kind of guess. First of all, v of 0 has to equal 0. We know that. And v of 18 has to equal 0. We know that. So I'm going to just try, v of 8 and v of 10. I would hope that v of 9 would be a max. It's not going to be, but let's just try v8, 9, and 10, and then it'll give us a start. So we pull out the calculator and just figure it out, right? So I'm going to say 36 minus, let's try 8 times 2. And then I'm going to square that. And then I'm going to times that by 8, because there we go. That's what we're looking for. So this is 3,200. I'm going to do the same thing for 9, and I'm going to get 2916. I'm going to do the same thing for 10 and get 2560. And I think, aha, well, this is interesting, because if 9 were the max, I would expect V8 and V10 to be less than V9, but it looks like we're getting better results by going further down. So 8 was better than 9. Okay, so we're going to try some other values. Okay, so let's try 7. Is 7 better than 8? Maybe, because we went down to 8 and we got a better value. 7 gives us 3388. Ooh, well, then the max, maybe it's at 7. So we try V of 6. And we get 3456. Well, that's interesting. So far 6 seems to be the winner. And so, I don't know, we could try V of 5. Alright, what's going on? Let's see. 36 minus 2 times, now 5 is the thing we're interested in, to the power of 2 times 5. And that's 3380. So V6 is definitely better. Let's try, if we're at 6, maybe 6.5 could be pretty good, or 5.5, or 7.5. Okay, and it turns out 6.5 gives us 3438.9. 7.5 gives us 3307. Okay, let's try 5.5. Alright, so we have 36 minus 2 times 5.5 to the power of 2 times 5.5. and then this gives us 37.5. Of all these contenders, let's see, we found that V6 was the biggest. Oh, no, actually, this guy was the biggest. Just a little hair more. Okay? So we searched around. We found that 6 was the biggest. 6 gave V the largest value. Except then we wanted to try nearby, so we tried, a little bit above, a little bit below, and we found that 6.5 was about right. So, okay, let's say Vmax is approximately 3439. Good enough. Okay? And I would not expect you to do this much hunting and pecking and guessing on an exam. I would give you more guidance on an exam. But I could say, try the following values. Plot it and try the certain values, and I might give you a list of 4 things to try. And here we did like 1, 2, 3, 4, 5, 6, 10 different things. It's perfectly valid for a homework, but on an exam I wouldn't make you do that many because it would just be a little bit time consuming. But I mean, the theory is not hard. You just have to sort of plug away at it. And it's nice to know that when you get to calculus, there's a technique that'll allow you to hone right in on the answer for this particular problem, and you won't have to do that pecking around. Okay? Let's see. Oh, yes.